We have introduced the equation to calculate the angle of twist or the deformation of a torsional element. Right, this is the phi, the angle of twist equals torque L over Gj. Right, the T is torque, L is the length, G is the shear modulus or modulus of rigidity, and J is the polar moment of inertia. Okay, knowing this equation, let's go through an example. Okay, this example looks very similar to our first example in axially loaded element, the deformation. Okay, in that case, we have this two-sectional column, and here we have a two-section torsional element, shaft. Okay, it's a compound shaft shown here, consists of a solid bronze shaft 1 and a solid steel shaft 2, as shown in here in this sketch. The compound shaft is subjected to torques at C and B of 300 and 800 respectively. To determine, of course, here in these three questions, the C, determine the angle of twist at C will be our final goal, right? But as some middle steps, we will also calculate the internal torques in shafts 1 and 2. Okay, then the shear stress. But we will not be clear that we will not need to calculate the shear stress so as to calculate the angle of twist, right? We only need the internal torques as shown here. We just need internal torques, then we'll have the length, the modulus of rigidity, and the polar moment of inertia. Right, so here we will just, according to the three questions, to calculate them step by step. The first one would be internal torques. Okay, we have just that steps, right? So we will need to run the free body diagrams to determine the internal torques. Okay, so to solve question A, we will start from free body diagram. Right. So for the element 2, let's look at element 2 first. Right. Cut it from here to make it free. So we will have to cut it off to get the free part here. This is the point C. Right. The TC is there. The TC, use our right hand rule. The TC should be pointing upward. Right, so this is our TC, the double-headed arrow. Then we add the internal torque T2 outward. Right, this is the T2. Right, from here, so we can write an equation that is what? That is TC minus T2 equals 0. Right? So T2 equals TC. T2 equals TC equals 300 Newton meter. Then the second one, we cut it from here to make it free. Then you will have TC here. TB, well, use your right hand rule, curl your fingers, and your thumb will be pointing downward, right? This is our TB, and the T1 will be here, right? So you will have TC minus TB minus T1 equals 0. So T1 equals TC minus TB. That would be 300 minus 800, or negative 500 Newton meter. So we're done with step A. Right? We have determined the internal torques in shaft 1 and 2. Right? Section B, the question B is not useful, right, to solve the angle of twist at C, but it's asked that we can just solve it. We solve it, so we have to determine the C values and J values, right? So here just a C1 is what C1 in part 1 in shaft 1, that is 35, right? 35 over 2, that is 17.5 millimeter, and J1 equals just pi over 32 d1 to the fourth, and that would be 147,300 millimeter to the fourth. Then C2 equals what? C2, the D2 is 25. That is 25 over 2. That is 12.5 millimeter. And the J2 is just a pi over 32, D2 to the fourth. And that is 38,350 millimeter to the fourth. So the tall one can be calculated as T1 C1 over J1. Right? So I will skip the calculations and tell you the result. But here, okay, based on our experience in the first midterm exam, it's important for yourself to try this out, right? To try to run these calculations and to check if you can get the same result as mine. Okay, so here's the result will be, I will give you the result directly and you try it out, right, to double check and validate, verify my result. Okay, here's the tall one can be calculated as 59.4 MPa, right, and tau 2 would be T2 C2 over J2, that would be 97.8 MPa. Okay, then let's look at the last step and our final goal to calculate the angle of twist at point C. Okay, so obviously here we will need to use the second equation, right? The second equation says phi equals sum of Ti Li over Gi Ji, right? Or phi 1 plus phi 2 in this example, right? But here just I will give you a note here. Sign is important, right? Positive or negative, you have to take care of the sign of these angles of twist. Okay, so let's look at phi 1. Phi 1 is just T1 L1 over G1 J1, right? So the T1 we have determined, right? T1 is here. T1 is negative 500 Newton meter, and T2 is 300 Newton meter, right? So here the T1 would be negative 500 Newton meter. Okay, we need to convert it into Newton millimeter. So times 1000 Newton millimeter times L1, that is 800 millimeter over this is G1 G1 is where? Here, 40 giga-PA, Okay, this is 40 again times 1,000 MPa times 147,300 millimeter to the fourth. Okay. Make sure that you understand why we need this two 1,000 here. Okay, this 1,000. These two 1,000 are used to convert Newton meter to Newton millimeter and convert GPa to MPa. Okay, again, this is just for that we can have consistent unit. Okay, in the whole calculations. So here the result will be negative. Right here, this is important. Sign is important, right? So this is phi1 equals negative 0.0679 radian. And in the same way, we can calculate phi2, that is T2L2 over G2 J2. Right, this is 300, so positive, right? This is 300 times 1,000 times 1,300 over 58 times 1,000 times 38,350. Right, so the result here will be 0.1196 radian. So the phi would be phi1 plus phi2, that is negative 0.0679 plus 0.1196. The result would be 0.0518 radian.